So hi again, everyone. Thanks for attending our half training day. Let me tell you a bit what we will do today, what's the plan. So can I assume that everyone in this room was present in my previous talk this morning? Because I'm assuming you know the general outline of what I gave, and now we will dive into more of the details. So I hope that everyone was present. So I'm, as you know, I'm Danny, one of the co-founders of Dato, and we have two aides here. We have Robbie, who is a grad student at the Hungarian Academy of Science. And actually, Robbie is probably shy, but I can say that he won 2 RecSys competitions using GraphLab Create. So he's kind of an expert. So when I learned he was going to be here, I immediately volunteered him to help with the training. And if you're interested in his work, we have also in our gallery code contribution that he gave us that explains the winning method in RecSys last year, RecSys competition. So that's one of my helpers. The second is Guy. Guy came with me especially. So Guy is a master at Ben-Gurion University for machine learning, and he's working with me for the last year or so, giving a lot of trainings and doing a lot of activities. So our plan for this afternoon is I'll start with around half an hour of some more deep dive examples to show you the different aspects of the product and the software that I didn't have enough time to dive into the details. So that will be like a 30-minute general overview. And during the time, Guy and Robbie will go around to make sure everyone who wants to actually try out the software during this training session will be able to do so. So it's not mandatory, so if you just want to look and learn without doing it, you can. But for you, it will be very nice if you can also install and play with the exercises and so on. So yeah, so I sent some instructions about how to install our stuff and some needed files. Anyone had a chance to install GraphLab? Oh, that's good. So anyone who didn't install GraphLab, let me show you what you need to do in case so we will be all on the same page. You just go to our website, dato.com, and then you go to a download button, and then you register. If you're a student, click on this link, and then you can have a free student version. If you're not a student, you can still get a free trial. So you register here. And once you register, you get access to the installation instructions. We have installers for Windows, Mac, and Linux. So anyone who wants to do the exercise, didn't install it yet, please do it now. And just raise your hand if you encounter any issue, something is not working. Guy and Robbie will come around while I speak. In 30 minutes, once I go over all the demos I wanted to show you, then we will start the actual exercise. The exercise address is listed here. So that's the short link. It's a PDF page. The exercise we'll do today is combined of 3 parts. The first part relates to data engineering. So it's slicing and dicing of the data. The second part relates to a bit of a graph analytics to show you how we can generate graphs on the fly and do some interesting analytics. And the third part is related to recommender systems, which are actually building models for user behavior. So that's the 3 parts, and we will have a break around 3. Any questions so far?
I think there is a typo there. The W should be capped.
Should be capped, you're right, should be capital.
Yeah, so please fix it, Guy. Very good. So let me show you some additional things. Yeah, so I want to show you a bit of one more additional demo, and then I want to show you the code, how we actually construct this kind of demo. So this is something I didn't show yet at my talk. I hope you can see it. So this is a demo from Amazon review dataset, which is focused around item recommendations. And what I can do here, I can put any item which is sold in Amazon. So I like Pink Floyd. And then the request is sent to the predictive server. And we got all the related items that are consumed by Pink Floyd fans. So I don't know if you can see the images so well here, but basically it's other Pink Floyd items and David Gilmour and so on. So this is a basic item-based recommender, which is not so surprising. But what I can do further, which is more interesting, I like stupid movies, Jim Carrey. So those are the kind of stupid movies that go together. It's Jim Carrey and also Rocky 4, Rocky 5 are all stupid movies. But now I want to see a movie watch a movie with my wife. My wife is way more serious. She likes Sense and Sensibility. It's a Jane Austen. What we can do, we can actually compute a path instead that we'll need to fight over the evening of which movie to watch. Then we can compute a path which links our preferences. And then we can meet in the middle and see some kind of romantic comedy, which is both stupid and dramatic. And that's why it answers both our tastes, hopefully. Sometimes when I give this demo, people tell me you're just lying. Your wife tells you what to watch and that's all, which is true. But it could help to try and relate us. So this kind of demo, what we see here, it has two elements. So the first element, we took Amazon review dataset in order to find relations between items, which items are consumed together. The second element is that based on this item relation, we generated the graph. And based on our two preferences, we look for the shortest path in the graph in order to link objects from different properties using the graph. So of course, it doesn't have to be items. It could be images, it could be stock market options and things like that. And that's a quick application we can generate with really a few number of Python code lines to generate. So this is what I want to show you now. Let me just operate my virtual environment. And what I'm doing here, I'm opening an IPython notebook. So for this demo, I will go quickly and show you how we generate the code for this demo. But in half an hour, you will actually yourself open an IPython notebook, and you will be able to use GraphLab yourself and try it out. So this is the IPython interface. Anyone here used IPython before? Yeah, so we have about 7 people, so it's good that I'm teaching, so let's say majority didn't use it. So basically, once I open an IPython window, I have these code blocks I can execute. When I press Shift-Enter or the play sign here, I can execute this code block. So the first thing I'm doing, I'm importing GraphLab. GraphLab is a fully supported Python package, and that's how we get all the functionality we would like to use. The second thing I'm doing here, I'm loading the dataset from the Amazon reviews. And let me tell you in a bit more detail what's happening under the hood. So I have a local folder which is called Data Amazon Reviews. And I load it into an SFrame. So SFrame is our scalable data frame, which is a tabular data structure. It's compressed column store, which is held in disk, not in memory. I can show you what it looks like. So basically, we have a table with different fields, like who was the user, what was the product, the title of the product, the time of the review, the score of the review, what was the text, and so on. As you can see, it's a rich table which has a lot of different types of fields. So it can have string fields, integer, floats, paragraphs, images, dictionaries, JSON objects. Everything is stored in this tabular data structure, which is the SFrame. And this is the heart of all our performance. All the algorithms are implemented on top of this SFrame. We have also a visual component if you want to look more quickly at the SFrame. So this is what we called canvas. The way to execute it, you can always have any type of data structure and just do .show. And when you run it, the canvas will open and you can see the different type of fields and their properties. So what do we have here? We have the different columns of the data. For each column, we build a quick histogram to show you what's going on in this column. So for example, the score of the Amazon reviews, there are 5 different scores, 1 to 5 stars. And we can see that 5 stars is the most popular, and then we have 4 stars, which actually means that people really like the items they buy on Amazon and review. In most of the cases, 80% of the cases, they really liked it. And in very negative, the number of negative cases is very low. Besides of the quick histograms, which are, by the way, computed very efficiently. So even if this file is 10 terabyte in size, and in a few minutes I'll show you a demo of a similar construction of processing very large file on my laptop, it still will return very quickly. Because we are doing sketches from the data, you can fine-tune the accuracy. But basically, we don't need to read all the data in order to compute this quick type of summaries. So we have a summaries of all the fields. We have also a tabular view, like in Excel, that you can see the different columns of this file. But what's more interesting is I can jump to any row, and this is unlike Excel, because Excel, when you get out of memory, your computer will get stuck. But here I can jump to row, I don't know, 400,000 or something, and then it will simply get brought from disk. So I'm not getting out of memory here, and I can jump to any row and look at the data. The last element that we have for data visualization is some basic plotting capabilities. So it is possible if you want to get some quick insights. For example, if you like to know what's the relation between, let's say, the score and the count of the reviews. I don't know, maybe it's complete. You see, so there are some statistics you can view, and it depends on the type of column. It may open different type of plotting capabilities that you can do, but it is easy to look at the data in different type of intersections in order to see what are the correlation of different fields. So this is the histogram statistic for the count, so there are more counts that are 5-star score, and so on. So that was a quick way of getting the look and feel of our data. That's what we call the canvas. And the next thing I want to show you is how we build a model for understanding what was the user behavior behind those Amazon reviews. So this is very simple. We have a recommender toolkit, and the most basic recommender is item-based similarity. So what I'm doing here, I'm basically generating a recommender module where I give the input is the same table, the same SFrame. And what's interesting here, that unlike all the machine learning packages you know, you don't have to explicitly convert this data set into numerical linear algebra. So you don't have to convert strings into consecutive IDs or categories into binary features and so on. We do all the conversion on the fly transparently. Of course, you can control how it is done, but we save this process. And this is one of the nice things that were mentioned in earlier talks today about the necessity of a lot of glue code when you want to use algorithm A and then get the result to algorithm B and so on. It's very difficult. You need to write a lot of code out after the method is used. In our case, each of the algorithms take a scalable S-frames, return a scalable S-frame, so it's very easy to concatenate methods. You don't have to work a lot on all the difficulties in converting this data to linear algebra. So what did I do here? I have item-based model. It's a very simple model. It just look on the two columns of this table, which is the user ID versus the item ID interaction. And I'm just comparing all pairs. So it's a very simple algorithm. The thing is, there are 200,000 items. So if you want to compare all pairs of items, it's a quadratic problem. So it could be time consuming, but still we implement it very efficiently and omit a lot of the comparisons that are not needed. So here I compare all items. In a few seconds, in 7 seconds, actually, I'm able to build the item similarity model. So let me show you how the model looks like. So the model is another S-frame, where it has the title of the item and what was the similar item find for this item. So basically, that's the output. So for a chronocross, we find one similar item with such and such score. So that's the output of the item-based model. So that was the first part of the demo, that if I like Pink Floyd, this is the kind of similar items, and this is the way it is computed by an item similarity method. Now I want to show you something which is a bit more interesting, how we can actually on the fly generate graph data. So that's very simple. Let's treat this table as a graph. So each row will be one graph edge between the title and similar. I don't need to save my data in graph format, which is add or snap or anything. I don't need to give consecutive IDs. I just I create an empty graph. I add the table as edges and point that the title will point to the similar item. So it's very easy. And it's a lazy operation, nothing happens here. I'm just preparing a data structure for graph analytics. So this is what we called S-graph, our scalable graph. Why are graphs very useful? Because we have a lot of graph operations you can use using this construction. So the most basic graph operation is shortest path. So let's now run shortest path. So I'm starting with some random item, and I'm building a spanning trees to all the other items. So basically, the graph is connections between items. Related items have an edge. Now, if I want to query this tree in order to find the shortest path, I can use the getPath call. And here I get the path, the full path on this shortest tree, on the spanning tree, which connects the two items. And this is the actual code which runs behind this implementation. So basically, the graphs are built dynamically. Whenever I select here two items, then we both build the graph, compute the shortest path, and return the answer to the user, and it's very fast. So that's how I do it using code. The last element of the demo that I want to show you briefly, but we won't get into detail in the training today, is the serving side. So we have what we call predictive server, which is very easy to spin up. In this case, I'm just connecting to Amazon. So I set up a predictive server there. And what I can do, I can name a model, which is SICS. And just to remind, the model was a Python object, which I generated earlier. So basically, any Python object, any Python function, any Python object from a different library, it doesn't have to be GraphLab. So if you're using scikit-learn, if you're using GenSim or any other Python package, it's very easy to ship it to the server. And what I need to do is basically commit the model to the server. And what's happening here, and that depends really on the internet speed here, and I think it's quite good, all the model is shipped to the server, and from that moment, the server will be able to actually serve the model in production. So this is an item-based model. I'm sending it to the server. From that moment, I can start querying the server, giving an item. I can find similar items, and giving a user, I can find recommended item for the user. So you see, the model was successfully uploaded. I have here 3 machines that are notified. So basically, it's an array of 3 servers. And I can show you how the deployment looks like. So that's another property of the canvas. You can also connect to the server and see what's the status of the server. So you can see it runs on EC2. I have a load balancer. That's the address of the load balancer in EC2. And the load balancer is needed if one of the servers die. I want to have the other servers take in. And I have the 3 instances that are now running. I can see the status of the instances. And I can see all the models that are currently deployed. So there are a few tens of models that are currently deployed with their versions. And I can also see all kinds of execution metrics. And in this case, nothing happened. So there are no metrics. But you can also see performance and so on. So once I set up the servers, I can query my model. And as you can see, I get a JSON reply. So the query is sent using HTTP. And I'm requesting recommendation for this specific user. Once I will rerun the model the second time, the response time will be even quicker because we have also a caching layer. So the bottom line here is that if you build some cool application, you have some very nice models, and you want to deploy them, you don't need to work 6 months in setting up server with database, with load balancer, with caching layer, with versioning, with all the application logic that needs to load the model. So if it's a neural network, it may be a complex logic that you need to implement code that loads the neural network from disk and does the scoring and returns the answer and so on. The server makes it way more easy to actually start deploying applications very quickly. Okay, so that's the first demo I wanted to show you. In terms of scalability, we have very nice demo, which is a quick video that I want to show you as well. Which is found or it was moved. Just a second. Where is it? Maybe here somewhere. Yeah, so this is our website. We have a very big gallery of examples. And it's a very easy way to start, where you have a task in mind. You should look at the gallery to see if there is anything relevant and related that you can try out. And once you choose some example, then it's very easy to just download it as either Python or IPython code and run the example, and all the examples are using public datasets. Yeah, so I think I'll skip for a minute the demo I want to show you with the video because I need to find it out. Guy, let me know if you find if you know where it is. But let me jump to a second demo I want to show you. So in this demo, the pathway is what we call, we have 2 basic functionalities. So one is related to recommenders, building an item model. And the second functionality is related to graph analytics. One of the things that I didn't show you at all related to text analytics, because we also work on text analytics. And because we don't have time for actually showing everything in a half-day training, I want to show you briefly just one example of text analytics we do. So you'll know it's there, but we won't have much time to get into the deeper details. So this example is what we call topic modeling. It's an unsupervised classification. Unsupervised clustering method. We want to cluster similar documents together. Again, I'm importing GraphLab, and here, instead of loading a dataset of reviews, I'm loading a dataset of text documents. So in this local folder, I have just a text file which contains New York Times articles. And there are 10,000 such articles. So the first thing I can do here is trim the document entries, which basically means computing a quick bag of words and removing the stop words. So all the words like and, de, and so on in English are kind of useless because they appear in all documents. They don't give us much information. So you can remove them. So that's what we get. We got a bag of words with, which is cleaner. And the next thing I want to show you is that we run a topic model. So this is LDA. That was also mentioned in some of the previous talks. So I'm now running it, and hopefully everything will run. Yes, something is strange here. That's the risk of giving live demos. Sometimes things are getting crazy. Yeah, so basically what I wanted to show you, if it was running, is that we run a few iterations of LDA, and the output is a few classes of documents. And in each document, we can see what are the relevant documents that are composing this type of class. Yeah, strangely something. My wish.
Can you stop and try with a smaller number of iterations? Test the making?
Yeah, yes. Yeah, no, something is strange here. Let me try again. Yeah, maybe I asked for too many iterations to be processed in a reasonable time. Oh, sorry. Yeah, so that was a good advice. I somehow missed it. So let me show you the results. So once I run LDA, we got a few clusters. I asked for 6 clusters. And I'm showing you cluster number 5, which has topics like company, government, plan, president, program, public official, which I don't know, it's intersection of business and politics, I guess. Topic number 0 is team, problem, system, market, Clinton, political, American. So yeah, let me run it. Let's do 10 iterations. Looks like it didn't fully converge yet. Let's see now. Yeah, so we have sports keywords like team, game, season, play, and we have some other yeah, so I can try to increase the number of iterations, and hopefully it will converge better. Yeah, each time that I run it, I get a different distribution of topic because it is a randomized algorithm. So yeah, but you got the idea. So this demo, the bottom line here is that actually you can also work with text as one of the, let's call it, equal citizens of our toolkit. So basically it could be text, it could be images, it could be strings, it could be dictionaries and so on. Everything is, we stick into an SFrame, and then all the algorithms can run on all the input files. So that's rather easy to navigate between the different methods. So let's maybe start with the exercise, now that I've shown you a bit of additional demos. So let me show you what the exercise is about. Yes. Yeah, so this is our exercise. If you like to follow up with exercise, you will need first to install GraphLab, as I showed you using the download button. And the second, you will need to download those 3 input files, which are originated from a Yelp public dataset. So that's something I assume you already done. Anyone who wants to try it out. So yeah, so let's do as follows. I will now take a small break to go around to make sure that everyone who wants to try the exercise has the right setup. And it will take like 5 minutes. And once we are all aligned and on the same page, we can actually start, and then I can do the exercise with you, basically. So go over the different commands and explain them and do it with you. OK, so let's make sure that everyone is ready. OK, so surprisingly, I think that 95% of the people managed to install and set up everything. So for us, it's very exciting. I think it's a record in all the training days. So it means we have very good audience today. So let me go over quickly what we need to do next. And let me find a way to show it more. Let me just show the exercise more nicely. Let me download. OK. So yeah, so the first thing you need to do, and I think all of you did, is install us and then run IPython notebook, and then you get the IPython interactive shell. The next thing you need to do is to press the new notebook button in order to generate a new notebook, a new clean notebook. And once you do it, you have to press a button to rename your notebook. So instead of untitled 0, just give it a name, in this case Danny, and press OK. And then you are ready to start working. The next thing you should try out is just write on the code box import GraphLab and press the Shift-Enter or the Run button. And if there is any error, something is not working, let us know, and Guy or Robbie will come to you. But it should work, hopefully. And once I open a new notebook, so I should be able to do import GraphLab. And if I'm not getting any error, then it's good. OK, so anyone has issues with importing GraphLab, or yeah, one issue? OK, so and also half an issue. OK, so let's assume you managed to import GraphLab. Let's go back to the exercise. Yeah. So this command is not mandatory. It depends on your system. You may want to have the visuals display inside the IPython, or alternatively, we open a browser for you to display the visuals. So that's not really mandatory. OK. So the first thing I want to show you, it's our first exercise, and the topic is data engineering. So as I told you, we have an open source project, which is called SFrame. And all this exercise discusses the open source functionality that we have. So the functionality are loading data, cleaning data, merging data from different sources, generating features, and doing all kinds of data slicing and dicing. So that's part of the open source project. So the first thing I'm going to do is to load this file that you should have saved somewhere. So you can give either a full path or a partial path in order to tell IPython where is your file. So I'm not sure if you saved it in this place or not. So what I'm doing here, I'm just loading a file. This is the read CSV command. It can it's not just CSV. It can also receive JSON and other formats, but the most basic is CSV. And it can also receive the compressed CSV, like in this case, which is gzipped. And this is our user information for the Yelp dataset. Okay? Anyone has issues with loading the CSV? Sorry? Runtime error.
It says
so.
.tgz in the help, but it's actually a CSV file.
Oh yeah, so it depends on yeah
Well,
on.
I got it as a CSV file.
Okay.
If you just take the TGZ,
Okay.
and it's trying to load a CSV file anyway, so I'm assuming it won't load a TGZ file if it's it. I assume it won't load it if it's it.
Yeah, so it should be a CSV, but I may have a few versions of this file which may be compressed or not compressed. So if there is any error, just raise your hand and Robbie and Guy will come to you. So I'm loading this file, and hopefully you managed to load. So the first command you can do is just look a little about the file statistics. So this is something I can do to show some statistic about this file. I think it should be included in one of the 3 files I send a link. Yeah. So as you can see, we can have quick statistics of the file. So we can see David is the most frequent user in this data set, and so on. So that's something you can play a little and look into the data. The next thing I want to show you is use the old pandas way, if you like, just to know it's there. So you can also see what's the head of the file and see some tabular listing of the file. So in this case, I see a very simple printout of what's going on inside my file. It's very easy to access specific parts of the information. So in many cases, you don't need all the columns. You want to focus on a single column. So for example, let's say you want to just look in more detail to the username. So that's very easy. It's like in pandas operation. So we treat the table as like a hash table. So you can access by the name. So it's user name. And then I get a vector, which is an S array. It's like one column with all the different names. I can see there are 43,000 entries here in the user list. And then I get some statistics. I get all the listing of the beginning of this vector of names, this array of names. We can also do all kinds of statistics about the S arrays. And in this case, let's see, I can look at the average star, for example. Stars. So yeah, on my case, it was loaded as float. So if you have an error here, you can always do something like average. If it's a string, you can always do as type int. Yeah, so you can do it like that.
Oh, sorry, this name.
Yeah. So what happens here is that you just treat the average star. I'm converting this array to another format. So I can say, oh, it was a string, but now I want it as an int. So that's the way to do it. Once I convert it to an int, we have all kinds of operations which are easy to do. So for example, if you want to know the average mean, yeah, the mean value of this column, so you can just do the mean operation. And by the way, in IPython, what's nice about it, you have tab completion. So you can also click to see why it's not identifying. Show a second. Yeah, something is not. Yeah, so for the SRA, for some reason, it doesn't recognize. But if you look at the table itself, there are a lot of functions you can use. So there is some interactive help. If you press tab, it opens the different. OK, so the next thing we want to do, for example, is not just to access a column, but we want to access a specific row, because we need some specific information. So what I can do here, I can just list the rows that are interesting to me. So let's say I want to look at rows 1 to 3. And this will list out the first 2 rows. OK? And you can do something like -3 to the end, and then it will give me the last 3 rows. And this is exactly equivalent to Panda's syntax. So those are the last 3 rows. It is, of course, possible also to get a different slicing. So if you don't need just specific row column, you need a combination. That's fine. You can always combine this operation. So you can access the last 3 rows, but then I want only the column name of the last 3 rows. So I can write the 2 operations on top of each other. The arrays also support all the logical operations. So if, for example, you're looking for, let's say, Tanya, and you want to find all the rows which contain information about user Tanya, what I can do here, I can create a new field, which is a selection, and then I can write user name equals Tanya, and then I can see all a Boolean operation which tells me whether this row contains information about Tanya. So that's kind of a slightly complex way to go, and then you can filter by this vector the table. But you can do also here a shortcut, so you can write it like that. So user name equals Tanya, and then that's the same, but concatenated. So basically, we have a Boolean operation which checks whether this username is Tanya, and then we select all the rows that match this criteria, and there is only one row, but let's look for Brian, and there are way more Brians than Tanyas. Okay, so yeah. And yeah.
Is there some keyboard shortcut to run?
To run, it's Shift and Enter. Okay. Shift Enter runs the code. Yeah. Okay. So you can also do more complex operations. So for example, you can look at how many users Jim, and their name is Jim, but also you want another criteria where their average star rating is above 2. So you can actually do more complex Boolean operators, logical operators, in order to find out. And I don't know why this, when you copy.
Yeah, we get that backtick.
Yeah, that's really annoying.
I've never been and never will make a review on Yelp. Life is too short.
Yeah, yeah. So here, what we did here is basically we have two Boolean conditions. The first is that username should be Jim, and the second that we want also the average stars to be more than 2, and then we end them together in order to find the right interesting data for us. Okay, so that was a quick way of just looking at the data in terms of the visualization and in terms of selecting specific rows that are interesting for us. But what we can do way more interesting things. So we have support for all the SQL primitives like group by, select, and join. And the way it works, we have our own syntax, but it's kind of similar to pandas. And what you can do is you can compute all kinds of SQL-like statistics. So let me show you, for example. Let's say I want to look at different names of people and count how many people are from that name. So this is very easy to do with the group by operation. And what we have for each user, we have how many are from that name. But let's say I want to actually find the top, who are the top reviewers in the Yelp dataset. So that's very easy. We have a command top k for that. And then I can do top k count, which actually will give me the user with the highest name, which there are 400 Davids in this dataset, listed in this Yelp dataset. So now I can count, and I can also, of course, reverse. So if I like to find all the users that appear only once, so that's very easy. So that's one thing I can do with the group by. I can also do more interesting group bys. So it doesn't have here to be just one column. So I can group by on name and I don't know, let's say review count. And here I'm looking for pairs. How many Davids that had review counts of 5? So it's a different time. You see? So, and then I can do again top k without the reverse. So I can know that John that had only one review, we have 80 people named John that given one review. And there may be other people named John who gave more than one review. Besides of the count, we have many other operations for the SQL functionality. So it's not just count. I can also do, for example, the mean of the star rating. Stars or star? Or score? I forgot what was the field. Oh, average star, sorry, average stars. What's wrong? Column name does not exist. Let's debug this strange error. Oh, sorry, yeah, I had a concatenation of commands, which did a little mess. So what I have here, I'm aggregating by two fields, name and review counts. And for the name and review count pair, I'm computing a mean value of average stars. So that's another. And you can go on and on with the group by because you can have multiple fields here, but you can have also multiple aggregates operation on the right-hand side. So you can also aggregate the mean and max and quantiles and all kinds of other stuff to the right. Okay, so we briefly touched some of the SQL-like functionality. In a few minutes, I'll also show you join operations a bit later. But this is a SQL-like functionality. What we can do further, which is also interesting, we can also do a lot of transformations. So if your data is not clean enough, you want to change fields, you want to remove fields. So for example, let's say all the users here are type user. So I have no information whatsoever in this column. So what I can do user remove column type. And now I get a new table where the column is actually removed if I don't need it. I can also do other transformation. So let's say I want to average stars +1. I want to compute the so I can do all kinds of transformation. What's even more interesting, I can also implement my own function which does all kind of data cleaning and other operations on the data. So, and this is called Lambda Function, and it's exactly like in pandas. By the way, if anyone has additional errors, just raise your hand and we have the help is still waiting to help you. So let me show you what's a Lambda function. So a Lambda function is a quick transformation that I can write. For example, let's say I want to have some cleaning operation over the average star. So I can implement it that way. So it's a Lambda function.
This could have saved Ashley Madison.
What?
You know Ashley Madison? The online cheating where,
Oh.
where there were like 6 million fake accounts. All they had to do was change the women had logged in, being true, and you would have saved the company.
Right. Yeah, so yeah. So what we can do here with the Lambda function, we can write any Python code inside this apply statement. So the function goes over only the column average stars and makes some transformation. So let's say I want the average stars to be 10 if x is equal or greater than 3, else I want it to be half x. Okay, so I invented some stupid transformation for the example, but what I can do here is apply this transformation to the full column, because this is some normalization I need to do. And then what's interesting about this implementation, while it's written in Python, we do parallelize it in a multicore. So, and this comes from pandas, but the difference versus pandas is that if you have 8 cores on your machine, you have a table with 1 billion rows, you write a Lambda function, you wait, only 1 core is active, and you wait a lot of times. And if you use GraphLab Create, then you have an 8-core machines, this operation is actually parallelized, and all the 8 cores will be 100% utilized, and it will roughly run 8 times faster than if you use pandas. So it's the same kind of syntax, but you have better speed up. Yeah?
Can I write transformation functions and have them execute on the cloud, fetching data from S3 and creating a model out there? If I know like it works on my local small sets.
Absolutely. Yeah. So we have ways for that. Let me show you. And by the way, feel free to ask questions because I like questions. It makes the discussion more interactive. So let me show you how you can do it. So basically, we have very good EC2 support. That's the cloud we support the best. And as I showed you, it's very simple. So you do import GraphLab. That's easy. But the next thing you do, you can do GraphLab AWS launch EC2 with which instance type you want to launch. And all the other commands remain the same, beside the fact you can direct your input and output to read directly from S3 and save to S3. So everything I showed you in this tutorial, you can actually connect to EC2 and run it there. Although it looks like it runs on your laptop, but when you execute, the command is sent remotely. Yeah, so there is a real distinction between where the code is viewed and where the code is run. And in this case, both of them in my laptop, but it can also run on EC2. Yeah. So let me see what else I wanted to show you in this exercise. Another way of writing the same Lambda function, I can also define a Python function. So I can call it define my transformation. And it receives a variable x, and then I can do return, basically the same code. And what I can do here is to apply a function my transform. Okay, so it's exactly the same. You can write any Python code and then apply it to your data, either to rows or columns or subset. What's more interesting, once we start to work with predictive servers, you can actually write your own Python code and then tell it, ship it to the server, and the server will start serving the code using RESTful API. So that's even more interesting thing you can do. Okay. Yeah. So you can do also column arithmetic, as listed here. So basically, you can do arithmetic based on not just +1, but you can do arithmetic based on a few columns, treat them as vectors, and do which kind of math operations you like. So if I want to do addition of 2 columns into a new column, then it's fine. I can do it. It will just sum up the values. Okay, so the next thing I want to do is to show you a bit more of interesting analytics. And for that, I'm going to load the 2 additional data sets. One of them is the business data set, and the other is the review data set. Let's see. Okay. Anyone has issues in loading those data sets? If so, just raise your hand and we will help. Okay, so in the help data, we have 3 types of data set. The first one was user table. The second one was a business table. And the third one was the review. And so there are 2 entities, users and businesses, and the reviews connect the business and the servers for defining the interactions, which users were in which businesses and how they review it. Okay, so I'm loading the business. Of course, it is possible, again, to visualize them using Canvas. So let's do now a small 5-minute exercise for you to actually load the businesses and look at their properties. And in a second, I will show you how we can also join table, which is one of the SQL primitives. So I'm going to do another quick tour to make sure everyone is... Okay, so now I'm back. I took 5 minutes, and I must say very good progress, so most of you are following. The last thing I wanted to show you is, in this exercise, is how we can join information, because usually our data doesn't come from a single table, but there are a lot of tables with the information. So what I can do is join tables based on a specific index. So in this case, I have one table includes only user information, and the other table includes only review information. So the review information has interaction between user ID and business ID, but we don't know the username because the user table has interaction between user ID and username. So what we can do, we can actually join those two tables in order to find the name. So the way is just like pandas, it's the same syntax. So you can basically join two tables. That's easy. And now for the join table, I can find all the records, all the review records for John or Jim or whatever. Okay, so now I got a richer table which contains additional fields. Let me do it. Yeah. Okay, so we are good. So let me start with part B of the exercise, but only for like 10 minutes, and then we will do a coffee break to get you refreshed. So let's start with the next part of the exercise. So, and some of you I know are faster than the others, so I saw you already doing interesting things. But for those of you who are still here, usually in graph analytics, we don't have a predefined formula of what is the graph. So usually the data is the real world data, and we are not sure what's the graph. And sometimes it involves a bit of imagination to actually decide what's the interesting graph in the data. So for example, if I have bank credit card transaction, you can say the graph is between the person and the store, but the graph could be also between the hour of day and the day, and the person and the store, and so on. So there is a lot of flexibility in many of the cases. So let me, before we will do the exercise, I want to give you a very quick demo of our graph analytics. And then we will make the break, and then you will do the second part of the exercise. So I just need to find out, where do I have it? No, it's not here. Oh, I have so many. Yeah. I think it's here. Yeah. Okay. Sorry, now I found it. So this dataset is a very small dataset. You don't have it, so we just look at what I'm doing, and then we'll make a coffee break. So the first thing I'm doing, import GraphLab as always. It's not interesting. What's more interesting is that I want to read graph information. And graph information is usually composed of two elements: information about the nodes and information about the edges. In our case, you can load it using two different files. So the first file I'm loading is information about, oh no, I'm missing a file. Information about some countries. Let's see where it is, sorry. Somewhere else. Yeah, so here is the right version of what I wanted to show you. Not this one. No. This one. Sorry. Yeah, so let me restart. So we go to the point that we want to load information about nodes. So we have a table of countries, and this is the table that we'll use for the node information. So we have countries: Argentina, South America is the continent, and the number of football championship they won. Okay, so that's a football data set. The other file I want to load is combines information about interactions between countries. That's the matches. And then we have, in each row, we have who was the loser in the competition, who was the winner, and what was the location of the football match. Okay, so that will be the edge file. So how do I construct a graph? That's very easy. I create an empty graph, and then I add the vertices. So countries is the table. I tell it what's the index in this table because there are different fields. And then I also add the edges. And then I tell it who is the destination and source for the edge. Okay, so that's easy. I just added vertices and add edges. The next thing I can do, I can take a look how this graph looks. So one of the properties of the canvas is that you can actually also see some graphs. Of course, not too big ones. So if it's a big graph, you will need to look at the neighborhood or small neighborhood. But it's very easy. Once you construct a graph, you can just do show, as I showed you earlier with data structure which are tabular that give you the statistics and so on. Also with graphs, you can see, and you can see that Germany in this data set is the winner of all the competitions because the arrows point to it, so they are the winning team. So one thing I can do, if I have a graph and I want to get back the data in a tabular form, again, it's very easy. I just write the graph name dot vertices, and again, I got a table. So it's very easy switching and transforming back and forth between the tabular form and the graph form. Because you may want to have a few tables, load them, join them, generate a graph, do analytics, and then get some data back as a table and so on. So it's very easy to switch. So I can just access directly the nodes and edges. One thing to note is that we have a few conventions that the node, we call it underscore underscore ID is the index. And the reason, I don't like it so much, but I complained a lot of times. But there is a reason. The reason is that we allowed graphs from different entities. So if the graph is shops and users that buy stuff at the shops, so the shop may have information like address and the shop size and number of employees, and the user information may have information like number of kids and age and things like that, which are completely different, but you want to construct a single graph. So username and shop name, it's different type of fields, and once you add different types of information into the graph, we need some agreement about what's the actual key for the node ID. So in our case, it's underscore ID. One of the interesting things you can do is treat this graph as a table, if you like. So if we have information on the nodes about the championship and I don't need it right now, so I can do remove column, and this column will be removed from the actual table of the node. I showed you filtering on SFrames to select rows and columns. I can do also filtering on graphs if I like. So I can do things like get specific vertices for the graph. So I can find a subset of the graph by the vertices, IDs. I can also do matching operations. So you can do things like get vertices by specific logical rules. So if I'm looking for all the nodes that are in North America. So that's something you can do. And it's kind of equivalent to the SFrame operation where you can filter by specific logical operations, but here the syntax is slightly different because this is a graph. You can also select edges, a subset of edges. And you can always select edges around certain locations, and then if you like, you can add the edges to another graph. So here I just selected subset of all the games that were in Rio de Janeiro, and then I actually created a new subgraph, which is not connected, but it has all the edges of the games in Rio de Janeiro. Another thing you can do, which is very useful for graph, you can get neighborhoods of certain nodes. So I can start with some target nodes. I want to know who played around the USA and Costa Rica. What were the other relations in a radius of 2. And then I can show you. So basically, we start from 2 seed nodes, and then we explore 2 hops in each direction in order to find the relations which are interesting for us. And this is something which is not that easy to do with the SFrame. So it's more natural to do with the graph traversal. Because in SFrame, you may need to join multiple times and so on. It may not be efficient. And here it is efficient. The last thing I want to show you before the coffee break is that we can also write our own graph algorithms if we're interested. So the most simple graph algorithm we can think of is just to count the degree of each node, which is kind of stupid, but it makes a quick example that I can show. So what I have here, I'm defining a function which is called countDegree, which receives a graph edge. So basically, it receives what was the source node, the edge itself, and the destination node. Once I get into the function, I would like to increment the degree. So for each edge that enters my node, I would like to increment my degree. I have one more neighbor for each neighbor. And then I just return the same. So I didn't make any modifications for the data. The next thing I need to do in order to run these graph algorithms is I create a field, which will be degree. So it's one of the columns in my table. And then I add it to the graph. So basically, I create a data structure that will have an empty degree field for all the nodes. So that's how I initialize the operation. By just writing, it looks like a SFrame operation, but basically I add it to the graph, so it is on the graph. And the next thing I like to do is actually apply this. So it's like a SFrame apply, but we call it ripple apply because it gets 3 values. So it's the kind of apply, but it runs on graph edges. And then I send the function to the ripple apply. And then I say what is the field that are modified in this operation. So they are the degree. And then I can show you the result. Oh, I forgot to execute. So execute. And then now we run in parallel using all my multicore, all my available cores. I run the count degree on this graph. And then I count. And then I see what's the degree. And according to our algorithm, Germany is the winner. It has degree 4. And of course, according to the picture I showed you earlier, that's correct. Germany, because she won the competition, it has the highest degree. So the algorithm is correct. OK, so let's do now 15 minutes break for coffee. And after the break, we'll do the 2 remaining parts of the exercise, which one of them is graph analytics, and the last part will be recommenders, or building models for user behavior. Yeah, so let's restart. And the next thing I want to do is actually do the second part of this exercise, which is graph analytics. And I want to show you how it's relatively easy to treat your data as a graph, even if it wasn't a graph originally, do some analytics and view the results. So the first thing I'm going to do here And the reason is that I want to be able to show you the actual results. Is oh, I think somehow I closed the right window I had open. Yeah, just a second. Let me reopen. Yeah, we were here. Okay. Yeah, I'm just reloading the data. Okay, so yeah, so the first thing I want to show you is how to construct a graph. And what I'm doing here, I'm just taking a part of the information so we can visualize it. So what we have here, we have the first thing I'm doing, I want to treat the year column as string in order that I will be able to construct a graph from it and concatenate strings and so on. And the second command, I am just adding edges. From the table I showed you previously that I joined the two data sets. So I'm adding a table with interactions between the year of the review and the name of the person who generated the review. So basically here I'm just preparing a graph. This writing means that I only took the first 500 rows in order so we will visualize it. But of course we can scale to way larger graphs. And one of the things I missed to show in the morning is some performance on really big graphs. So currently the largest graph we experimented with is Common Crawl. It's a graph with 130 billion edges and 4 billion nodes, and we can run it on a single multi-core machine. We can scale because we can scale it from disk. And it takes 9 minutes to run PageRank per iteration on this graph. So we can really scale to state-of-the-art graphs. So what I did here, I prepared the graph. And the next thing I want to do is actually show you how the graph looks like. And this is kind of the fun part of graph analytics, that very quickly some patterns emerge that if you don't use graph analytics, it's harder to visualize. So in this case, it's kind of a stupid example. I don't see here a lot of deep meaning, but what I did, I just took the names of the people who were active, and then I plotted an edge to the year they were active in. So you can see we have here a few years, 2007, 2012, and so on. And that way, I can actually start seeing communities of specific users who are active in specific years. And the way I did the graph more interesting interactively, we have a flag which is called the label hover, which means only when the mouse is on top of the node, the ID of the node will be shown. And this is the label content, so it's like the ID. Okay, the next thing we can do, we can actually do graph analytics. So the most simple, basic, and commonly repeating graph analytics is the PageRank algorithm in order to rank the importance of nodes based on the connections and assign each node a number which signifies the connectivity of that node and how much it's important in the graph. So what I'm doing here, I'm calling our graph analytic toolkits. We have algorithm implemented for PageRank, and you just give the input graph, and we run PageRank for you. This version is unweighted. We have also a weighted version, so you can also have graph weights. edge weights to the computation. So this is the result. This is a model, a PageRank model. And the next thing I can do here is show you what are the most important nodes. So that's easy. What I'm doing, the model has a few fields. One of them is what was the PageRank. And then I can simply reorder them by the importance. And we can see the winner is Mike. And there's someone named Mike who had the highest PageRank at 0.19. Yeah, so I can show you in the graph who is this guy. And that's exactly what I will do next. So what I can do if I want to show it is basically I can add the information back to the nodes in order that I can plot this information back. So what I'm doing here, I'm just saying, let's use this table as additional information for the vertices. So besides of what they had before, we also have a mapping between the ID of the node and the PageRank value. So it's very easy. I just remap this information back into the vertices. And the next thing I can do is again show the same graph, but this time instead of using the node label, I'm using the PageRank label to show you what's the PageRank value. Okay, so now the graph is being replotted. And now if I click the graph, I see the actual value of the PageRank and not the name person, but the value of the. Yeah. Yeah, so of course the PageRank relates to the graph structure. Yeah, so this is Mike. He's here. Mike is here. He's somewhere in the core of the network, but it also depends on the direction of the edges. So that's how PageRank works, but he's here. Okay, one thing I wanted to show earlier before we get to the last part of the exercise, I want to show you a real quick example of how SFrames are really, really scalable. So let me find this. Tray SFrame. Yeah, so this is the blog post. And let me full screen is unavailable. That's strange.
I think if you press on the YouTube side.
Oh, yeah, so I see the resolution is not that good here. No. Yeah, so maybe I won't show it, but because of the resolution issues. But in a nutshell, what we have in this video, and you can also look at later on your own machine, it's on our website in the blog, is we load a data set which is originally a text file of 10 terabytes, and we can actually do many of the operations I showed you about SFrames on this file, even if it doesn't fit into memory. So originally it's 10 terabytes. It has 1 billion rows. It has 1,000 columns. It's a dense table. But still, all the operations that I show you that we can sum up columns and do lambda transformation and so on, all the operations take around 2 seconds per operation. So if you sum up 2 columns, it will be 4 seconds, and so on. So if you like, you can take a look later. Apologies for the resolution issues. So let's get back to the exercise, and this is the last part of the exercise. So here is actually something I want you to do on your own, and I will make sure you're not getting stuck. So basically, the functionality of what we call the recommenders is a way of modeling user behavior. So the idea is that we have interaction between users and items that were consumed, and we'd like to find some condensed model which explains relation between users, relation between items, and can predict what's the next item that will be purchased or liked by any user. The typical metric that we use following the Netflix competition is root mean square error. This is what we'll compute here. But of course, we have also other metrics like precision recall and so on, which are supported. The basic functionality that we will use here is matrix factorization. It was also mentioned earlier. In some of the talks, you mentioned the ALS in FlinkML. We have, besides of ALS, we have 3 different algorithms implemented. So we have ALS, but we have also stochastic gradient descent, and we have a third one, which I forgot. Besides of supporting the matrix itself, matrix is kind of a simplistic data structure, but it holds only information about the user and the item. We also support more wide tables where you have information, for example, about the user. So it could be user age and zip code and number of kids and shoe size. And it could be the item color and shape and price. And also richer set of information about the user-item interaction. Not only the user bought one item or liked one item, you know what was the time of the purchase, you know what was the amount of the purchase, you know all kinds of information, whether the user was at home or maybe used the cell phone. So this way, we actually use a richer set of information in order to build a model. So this is something we support and not supported in the other packages. And there are algorithms for that, like factorization machines that can take into account all of those side features. So what we will do in this quick exercise, we'll just load this dataset, which we already loaded for the review. We'll split it into train and test. And then we will learn a model to try to predict the star rating score. The star rating score is between 1 to 5. In the first construction, we don't use the side data factorization. And next, you can also utilize the side data factorization, and you can also add information about the users and add information about the item. So basically, we link the 3 different tables into the algorithm, so we throw in more information. One thing to be careful here, first you don't want to overfit, so sometimes you have a lot of information not that useful, so you have to be careful. And sometimes when adding, for example, user information, it helps, but when adding business information, it doesn't help so much. So I will let you play with the different options, so you can try out with user information, without user information, and with side data factorization and without, in order to see which option will work the best in this case. Okay, so I will let you try it on your own. And once we are done with this exercise, we conclude the training for today. Anyone who didn't take my business card should do so. So I would love to give my email to anyone if you try us out, you encounter any issues. We would love to stay in touch. And again, I remind that we have academic, anyone who's working as a researcher in a university or a student can get a free license. So we'll be happy to grant licenses.